The climate changed after the melt started. The climate change didn't cause the melt caused the climate change. A simple model like temperatures rose and the ice melted is also not good enough. The temperatures rose after the melt started. So it reminds me of the quote by H.L. Mencken, for every complex problem there's an answer that is neat, simple, and wrong.
This is Climate Debrief, brought to you by the CO2 Coalition. I'm Angela Wheeler. In a moment, we'll be having a conversation with Dr. Koen Vogel, who earned his Ph.D. in geology from Penn State in 1991. Since retiring, he has returned to his early interest in climate change, particularly the melting of the last glacial ice sheets. So we asked him to do a short presentation on the subject. Dr. Vogel, thank you for lending your expertise with our Climate Debrief audience.
Well, thank you for inviting me. It's something between a major interest and a minor obsession with me, the Ice Age. There's a lot of information, and I'll show you a lot of it today. But what I'll be presenting today is mainly not my own work, but other people's work. It's peer-reviewed literature.
Given the title of your presentation, what caused the end of the last glacial, why don't scientists have a clear answer to what ended the last ice age?
You'll notice on some of the slides like this one, there's a reference to, for example, in this case, Arthur Dike's work in 2004. Arthur Dike reconstructed the ice sheets over North America. And you'll also notice sometimes there's a funny little 22 Ka, something like that, notation on a slide. Ka stands for thousands of years. So this is basically what the ice sheet, the North American ice sheet, looked like at the last glacial maximum. So when the glacial ice sheet in North America reached its maximum extent. Back then, you'll see most of Canada and a large part of North America or northern USA was covered by a thick ice sheet. I've added M, C, and V from Montreal, Chicago, and Vancouver. To give you an idea, the ice sheet was about 3 kilometers thick over Montreal, and Chicago was about a kilometer thick, so think about twice the height of the Willis Tower.
Why is it that some scientists think they can predict with great precision climate in the future when they don't know what happened in the past?
So what caused the big melt? That's what we're going to discuss today. And you'll notice I included a weasel word. We collectively don't know. So is there no answer to what caused the last big melt? Well, there's too many answers is our problem. We collectively don't know because we each have our own little opinion. Some will say, oh, it's the solar insolation variations, Milankovitch cycles. Some will say, well, it was CO2 that did it. Mainstream science has been trying to frame innocent bystanders in the big melt. As you'll see some of the work that's been done, which proves that it wasn't solar insolation variations, it wasn't CO2. But everybody has an opinion. Your Uncle Bob, after 2 drinks, he'll say, well, it was a squirrel that put an acorn in the ice sheet. I saw it on a movie once. Everybody has an opinion, but the simple answers, even the simple answers, are not good enough. If you say, well, it was climate change, the New York Times approach to everything. The climate changed after the melt started. The climate change didn't cause the melt caused the climate change. A simple model like temperatures rose and the ice melted is also not good enough. The temperatures rose after the melt started. So it reminds me of the quote by H.L. Mencken, for every complex problem there's an answer that is neat, simple, and wrong.
Most of us picture the Ice Age as a time when everything was just frozen and cold. In simple terms, what actually happened when the world started warming up and the huge ice sheets melted away about 20,000 years ago? How dramatic was it?
Well, it wasn't dramatic. You see here on this slide, this is what Europe looked like during the last glacial maximum. You see a thick ice sheet covers Scandinavia, most of Britain. And you see below that, there's an orange zone which I've labeled tundra. This is a slide, by the way, that I took from Anderson and Bournes, which is a very good reference for people wanting to learn more about the last ice age. And you see, the area just below the ice sheet is called tundra. That's a very cold, dry climate zone. It's not very comfortable living there. And below that, you have something called steppe and parkland. And that's where, if anybody was alive back then, that's where most people were living, you see. Around 22,000 years ago, the cave paintings in Lascaux were created. And you had a very small settlement of hunter-gatherers in Ohala too. But 6,000 years later, it wasn't much difference. You had some cave paintings in Fond de Gaume, which is near Lascaux. And they were still living in caves. What happened is the glaciers melted, the ice sheets melted, the climate changed. They became mainly warmer and wetter, and CO2 rose. The CO2 rising is also very important because CO2 is plant food. And back during the Ice Age, the CO2 concentrations were so low that plants were struggling. Humans, plants, animals, everybody was struggling back in the glacial days. And then the climate change happened, the big global climate change. The global temperatures rose 4 to 6 degrees. The precipitation started to increase again. It all happened due to natural factors. Humans were, some estimates are as low as 50,000 humans living on the planet back then. It wasn't a good time for humans. Then the glacial period ended, and all of a sudden we started prospering again. The warmer climate, the wetter climate, humans started prospering. The sort of center theme of today's presentation is that the current climate models cannot simulate the last deglaciation, and I'll show you why in a minute. But the current models, such as the models used by the Intergovernmental Panel on Climate Change, they have one really big knob labeled CO2, and climate modelers like to play with that one. There's a smaller knob called solar insolation, sunlight, and you can play with that a bit, but you have to be really careful because we don't really have much information about how sunlight changed further back than the satellite era. And there are some smaller buttons, which we won't get into today, labeled volcanics and aerosols. And but the main one that climate models like to play with is called CO2, and you can ramp it up 4 times, or you can drop it back to glacial times. But you can't model the deglaciation. You can't model the big melt. Nobody comes even close.
These graphs show the central mystery this discussion is built around. Why do these massive ice sheets disappear so abruptly and so regularly every 100,000 years?
So what you're seeing here on the left is, on the horizontal axis, there's a time scale, time thousands of years before present, and it goes from, on the left, the present day, 0, to all the way on the right, 1 million years ago. And on the vertical axis, what you see is a proxy, so something which demonstrates the ice volumes on the planet. You read the curve from right to left, so you see there's these deep dips in the curve. Those are the interglacials, periods between glacials, the warm periods. And you'll see that immediately after the glaciers start growing again, and for the last 50,000 years of each little cycle, each little peak, the glaciers keep on growing and growing and growing, and until all of a sudden it drops off again, giving like a sawtooth pattern to the whole thing. You see, each of the G's I've put up there, that represents a glacial period. And they come and go every 100,000 years, which is a problem because we don't know why. On the right curve, that's a zoom up of our recent period. You can see up until about 20,000 years ago, the glaciers were still growing. And then all of a sudden, around 19,000 years ago, the glaciers started melting, and melting fast, vigorously. And then we descended about 10,000 years later into our current interglacial period, where the ice sheets have largely disappeared.
In the 1970s, there was talk about an ice age. Why would scientists have thought that there would be an ice age?
Well, at the time, we'd had some very cool periods, cool weather periods. They weren't really climate change, but people were concerned that this might be a return of the glacial period. And you notice, I use the word interglacial. We are still in a glacial period. We still have ice caps. The interglacial period is a period between glacials. So based on past experience, the left curve you see here, we're expecting another glacial sometime. Why people think they were going into an ice age, we had some very, very cold winters, and people always like to panic and spread prophecies, and maybe if they come true, they'll establish a name for themselves. But 1963 was a very, very cold year, but it was just simply cold weather. It wasn't a climate change. It was just a very, very cold winter. And as we went to the 1970s, it still remained quite cold. Around 1980, temperatures started picking up again, and we abandoned glacial for global warming, and that's where we are still today. The temperature's still rising or plateauing.
And from your understanding of that, was that stated as human-caused, the way they're saying that the warm weather is human-caused?
Well, it's hard to argue it's human-caused cooling. There are some people who suggest aerosols and that sort of thing might have been sulfates, might have cooled the climate during the 50s and 60s. It's really very uncertain, if you're honest. The climate models are not at the point where we can actually pinpoint what is causing some of these weather effects. They're not really climate effects. They're more like cold weather can happen by happenstance. So we had a very cold winter in the U.S. This year because of a polar vortex came down. And these are weather events. When it happens over a longer period, then you can call it a climate change. But you shouldn't confuse the two.
In your presentation, you state what you call inconvenient facts. Why do these facts make it so hard for scientists to figure out what really ended the last ice age?
Well, as I said, a lot of people have answers, but they don't have the correct answer. A lot of these inconvenient facts directly contradict the answers some would like to give to the problems of what caused the big melt. So one of the very inconvenient facts is that it was a global climate change that happened, and it happened synchronously on both hemispheres, North and South Hemisphere, which is kind of incompatible with people who like Milankovitch cycles and solar solutions, because those solar solutions often favor one hemisphere over the other. It happened very rapidly between 17 and 14,000 years ago. This is according to Brucker and Denton, who were two of the greatest climatologists who ever existed. There was really vigorous melting, which started before the climate change happened. So 17 to 14,000 years ago, climate change. But by 19,000, the ice sheets were melting under a very cold climate. Both Europe and North America were in the oldest, driest, which was a very cold period, 20 degrees Celsius lower temperatures than today. So how did that happen? It's a big mystery. Massive meltwater floods up to 20 Sverdrup. Now, what is a Sverdrup? It's 1 million cubic meters of water per second flowing through somewhere. And it's actually mostly used in ocean currents because ocean currents are much bigger than river currents. One Sverdrup is about the combined output of all the world's rivers at this point in human history. So 20 Sverdrup is a really, really, really big flood. When climate modelers play with floods, they'll add maybe 0.1 Sverdrup a year, or if they're really feeling naughty, they'll go up to 2 Sverdrup. 20 Sverdrup is a huge flood, which is bigger than most climate modelers can even imagine. And that was happening around 19,000 years ago. The Patagonian ice sheet in the southern hemisphere, so think Chile and Argentina, it was also melting at that time, which is really inconvenient for people who like solar insolation solutions, because typically it's either the northern hemisphere or the southern hemisphere, but not both. And both were melting before the climate change happened. And then you have the Greenland ice sheet. It hasn't melted. It received the same amount of sunlight as Scandinavia and northern Canada did, but it didn't melt. And the CO2 has doubled since the last glacial maximum. Atmospheric CO2 has doubled, but it still hasn't melted yet. So people who like CO2 and solar insolation solutions have to explain why these inconvenient facts are there. And they'll sort of, if I just sort of, and they'll hem and haw and try to work their way around these. But your explanation needs to explain these facts. The last one is my personal favorite. Climate change and the paleogeomagnetic field intensity co-vary with 100,000-year cycles. So this typically will cause people to just stare at you with a Bambi in the headlights look, because the geomagnetic field doesn't covary with either CO2 or sunlight. So why it is covariing with things like the Southeast Asian monsoon rainfall, as Zhu and his colleagues claim, is a mystery. It takes you in the wrong direction of the way you want to go.
On this slide, your graphs from Antarctica show that when the last ice age was ending, the planet started warming up and the big melting began. But carbon dioxide levels in the air only rose hundreds of years later. You even have a note asking, what about Greenland? Can you explain why CO2 didn't play a role?
So let's start with the graph that's up top. You'll see, once again, on the horizontal axis, its age. Starts at 0, so the present on the right side, and 800,000 years ago on the left side. You'll see the red curve is a reconstruction of the Antarctic temperatures, and the blue curve is the reconstructed atmospheric CO2 from the ice cores that were analyzed. And you look at the graph and say, bingo, we have a winner. It's the covarying. But the problem is that CO2 doesn't covary with anything else. It covaries strongly with Antarctic temperatures, but the CO2 increases are 400 to 800 years after the temperature increases. So the cause must precede the effect. The effect must lag the cause. The Antarctic temperature rises cause the CO2 increases. And how people think that works is you have big, cold upwelling currents near Antarctica, which bring cold, deep, CO2-rich water to surface. The water heats, the CO2 gets degassed, and that increases your CO2. Cold water dissolves, CO2 dissolves in cold water much better than in warm water. So if you bring a cold water mass to surface, it will degas. Similar like your beer or your cola in a warm pub. You leave it standing and it will degas. The cold Coke will lose its CO2. The graph below shows, once again, the transition from glacial period to interglacial period, 6,500 years ago on the right to 22,000 years ago on the left. And you'll see the yellow dots are CO2, and the red curve is Antarctic temperatures, and they track each other fairly well. The blue and black curve is the global temperature reconstruction, and you see it doesn't match CO2 at all. CO2 started to increase before the global temperature started to increase. And what's really peculiar is the vigorous melting that I was talking about. It started 19,000 years ago, and it predates any CO2 increase, and it predates the global temperature increase. So I have the green arrow up there, which is Brucker and Denton's climate change dates, 17,000 to 14,000. You see that matches fairly well with the global temperature increase. But the melting started before then. It started before the temperatures rose. It started before the CO2 started to rise. It started before anything. So what about Greenland? That just means, we had vigorous melting happening at latitudes where Greenland sits at. So why did one melt and the other and Greenland not?
What's wrong with Milankovitch cycles? These are commonly cited as causes.
Okay, so this is a very popular explanation of why the ice melted, but it doesn't fit anything. It doesn't fit the data at all. So Milankovitch cycles are due to the changes in the Earth's orbit around the Sun. And the two most, we call them orbital forcings because they force climate change. So you'll have precession, which is basically the Earth's axis describes a bit of a circle relative to fixed stars. It makes a bit of a path like a circle. It has a 20,000 year period, and obliquity is just basically the Earth's actual tilt. And it has a 41,000 year period, but they're too short. We're looking for something which has a 100,000 year periodicity, and they're just too short. And besides, the ice sheets grew for the last 50,000 years, so they survived 2 precession cycles and 1 obliquity cycle and didn't melt. So many authors like eccentricity. The zoo article I mentioned before, they attribute the 100,000-year cycles to eccentricity, but we'll see in a bit that doesn't work. Eccentricity actually has a 400,000-year cycle and has sort of pseudo 100,000-year cycles, but it only minimally varies solar insolation. So it'll increase the intensity of the sun by minute amounts, which are insufficient to cause melts. There's a third orbital forcing, but it's not a classic Milankovitch forcing. It doesn't alter the sunlight much. It's called orbital inclination, and it has a 100,000-year period. It has an excellent fit to deglaciation cycles. Miller and MacDonald proposed this 30 years ago. But it doesn't vary solar insolation. It's only even less than eccentricity, very, very minimal amounts. It does vary Earth incident solar wind. So the solar wind is charged particles that the sun sends at us. But the power of the solar wind is many, many magnitudes smaller than solar insolation. So that's not a solution either. The orbital forcing either fits or the solar insolation fits, but not the two. You can't have a 100,000-year cycle. You can't have a 100,000-year Milankovitch cycle, a classic Milankovitch cycle that alters sunlight. So this is eccentricity. What I've done here, this is my own plot of data from Lasker et al., Lasker and his colleagues. They went to town and calculated the solar intensity for many million years in the future and the past. And this is basically what goes into the climate models. So you can see eccentricity has a 400,000-year cycle. It's been up and down a bit. And the red boxes are the interglacial periods. So you can see in a glacial period 11 started at a very low eccentricity, and 7 started at a very high eccentricity. There's no correlation between the two. Eccentricity doesn't work. It's insufficient. It doesn't change solar insolation much, and plus there's no correlation at all apparent.
Regarding this graph, why do you say these orbital changes still aren't the real reason the giant ice sheets melted away so fast?
Okay, so once again, on the horizontal axis, you have time. So on the left, present day. On the right, 800,000 years ago. And on the vertical axis, you have solar insolation at high northern latitudes, at 65 degrees north, which is sort of where the ice sheets were sitting. And you can see that the solar insolation at that latitude varied a lot, significantly, but there's no apparent correlation between the start of a glacial period. The pink boxes are once again the interglacial periods. You can see, for example, interglacial 11 started at basically a very average solar insolation. It never really got very high during the entire interglacial, and it ended at the same solar insolation. Now, 11 is a special case because it resembles our current interglacial a lot, and it was known for its warmth. It was 2 to 3 degrees warmer than it is today. It's known for its high sea levels, up to 20 meters higher sea levels than today. And it was also noticeable for its length. The interglacial lasted much longer than other interglacials. And that despite the fact that solar insolation wasn't really much, was very low. It didn't change much at all.
In this slide, you state melting started before climate change. Why do you say these solar insolation changes still can't be the main reason the ice sheets melted away so dramatically every 100,000 years?
Okay, so what you see on this graph here is, once again, on the left, present day. On the right, it's 125,000 years ago. So it's basically a zoom in to the solar insolation curve I showed you in the last slide. And the blue line is the Greenland temperature reconstruction from the NEEM group. And you can see that Greenland temperatures range from very cold to extremely cold, minus 30 to minus 50 degrees. Temperatures didn't rise above zero for most of the last glacial period in Greenland. The black curve is once again the solar insolation curve, and you can see when the ice sheets in Western Canada started melting 19,000 years ago, the solar insolation at high northern latitudes was below most of the glacial is around 490 watts per meter squared. Well, the peak immediately before it went up to about 510 watts per meter squared. You can also see at the time of the melting in Western Canada, the Greenland temperatures were actually at somewhat of a minimum. They were very, very cold. So both don't fit a model that supports solar insolation.
We hope you'll join us next week to hear part 2 of my interview with Dr. Koen Vogel.
Thank you for joining us on Climate Debrief. Executive producer is Angela Wheeler. Producers, Ethan Audie and Scott Wheeler. You can find more episodes of Climate Debrief at co2coalition.org.